Hello, YouTube viewers. Welcome to my show, Future Friday. In today's episode, we're going to discuss smart materials. So let's dive right into it. Well, first we have to understand what the heck we are talking about. We are talking about something that is normally static, as in it does not have moving parts. It's not a micro material where it's like actually changing physical shape and size, like a gear or rotation, things of that nature. All things happen to static. If it's happening to a static material, as in like a lump of object that still remains a lump of object, then you will classify as smart object. Basically, it's not physically moving or changing. Then, of course, the ability to change material. Otherwise, it's just dumb material, but it does require external stimuli. So you cannot have something, let's say, like tar, where it over time changes its shape. No, not something like that. It must do that over in the case of external stimuli. Now that stimuli could be anything. For many things it's heat, for some things it's electric, for other things it's magnetism. So it's up to you. Now generally they are designed to be reversible. Now that is the crucial aspect here, because again, this sort of coffee mugs are awesome, but here's the deal: it would be meaningless if it can be done only once. So it must be reversible. So it's not like okay, ice melting, because again it will not freeze up again automatically. You have to put it in a freezer. So it must be reversible and it must be static. So you can see, like, the paint will not turn to liquid and then where you can wipe it off. It will remain a static thing, even though it's going through change, but it will remain static. So how does it actually work, like this kind of magistical thing? Well, again, everything requires energy. So you must understand the stimuli that I'm specifying is not something like, okay, it's just there to trigger it. That will happen if it's a mechanism. To actually change it, it utilizes that energy itself. For example, you take a spring and you want to make the shape out of it, or you want to use the have a deformed spring that in case when you heat it up, you change it back to the required shape. Now how the heck you will accomplish that? You need energy for that. That energy would be the stimuli. So for memory metal, things like that, there would be like 200 degree, 500 degrees Celsius. There will be again, whoever the manufacturer is, whatever alloy that is, there will be a description. It's like at this temperature it will retain its shape, at this temperature it will change its shape. So you will have that heat would act as the energy source. Even in case of, like, say, magnetic fluid, the magnetic field itself is providing the energy. So that's the whole thing. You must provide energy externally. Then it has no moving part. This is where, like, you can't have a gear or rotation, things of that nature. That will not classify as smart material. Now, changing of state. Now this is a very critical aspect. You must understand, when you see a paint that is changing based on temperature or something like, and if it's a smart material, it's not changing by melting. It's not a changing state. Basically, if this is solid, it will remain in solid. It will not go to liquid. If you are talking about magnetic fluid, it will remain a magnetic fluid. It will not go from liquid to solid. So that is one critical aspect. Now there is a limitation to this. Most of the time, almost 99.99% of the time, there are only two states. You can have, like, either on or off kind of scenario. You cannot have, like, okay, if you, let's say you have this spring, you heat it up to 100 degrees Celsius, it will say hello. Heat it up to 300 degrees Celsius, how are you? It's not gonna do that. There is only generally one state. So what is the science behind it? Where is this magic memory metal is happening? Well, you have to understand that even though when you think of something as solid, be it steel, be it aluminum, be it whatever it may be, generally they are not fixed on their states. Think of it this way: if you ask anyone who works in metal shop, is like, hey, what is the difference between this metal and that metal? Most often than not, it will be like, hey, it's been tempered, it has been squashed again and again, it has been hammered, it has been, basically you treat it. You don't magically take, okay, this metal will be strong. You take it and you treat it. Depending on your treatment, you will get the output. Now if you want a spring, you will treat it differently, so you get sponginess. You want to make it like hardened steel, you will treat it differently. Now where the heck that is happening? If the material is the same, that means, let's say it has this amount of alloy, like it has with this amount of iron, this amount of carbon, this amount of zirconium, whatever have you. If that is not changing, how the heck the property is changing? Property is changing on what we classify as crystal structure. Because if you go down to, basically, let's take a microscope and you start to go down, before you reach atom, before you reach even molecule, there is a crystal structure. So now that structure is where all this smart material magic is happening. You are not going down to basically atomic level, where you are chemically reacting with something. You are going down to crystal level. So you have solid, you have crystal, then you have molecules, then you have atoms. So you are dealing with basically crystal level. That is where all the magic is happening. All the designs are on that crystal structures basically. And in this basically crystal structure, you have your defined properties. Basically, if you want to your object to retain back its shape must be inscribed in what we call crystalline solid. Basically, if it's perfectly aligned, it will happen this. Now what happens when you deform it? You change the crystal structure. When you heat it up or apply electricity, apply magnetic field, you rearrange them. Now based on the chemical interaction, basically molecular interaction, they generally try to go back to the same state, basically crystalline solid. This is where the magic is happening. This is where you need your PhD in order to make a memory metal, so to say. So again, this is something, it's very complicated. Like even studying normal metal grains is complicated. Understanding these hobbies are completely different, and they have been used in ICBM warheads. So they change their, because once they're going up, you don't want them to have same shape, but again you want their shape to change once they're entering the atmosphere, because exiting it you wanted a different shape, entering it you wanted different shape. Again, memory material, because during re-entry it's really hot. So what are the use cases of it? Okay, we can make this, we have been making this, and again there are many principles behind it. So what the heck we do with this? Well, I have to give kudos to whoever the engineer or PR manager is in SpaceX. They come up with this amazing mug. You have this mug, it has basically Mars on it, but when you put hot coffee, it will warm up the system and you will get completely different image. And that's amazing. That's technically that's the same. We want to heat up Mars and we can make it quote unquote livable again. So quite amazing thing. Like it's smart, like respect. And then you have other things also, basically, where you have a thermal sheet where you can see thermal properties. You put your hand, it will act like a physical infrared sensor. You want to test out like how heat pipe is conducting, you can use that. So a lot of study tools and aids are also made on smart materials. Now there are hundreds of other use of that, but none of them are so significant whether I say it and you will understand it. Like even I like it's very obscure. However, in aerospace industry, it's becoming very prominent now. Many of the times you have to understand that airports are generally like people want to build it outside of the city, but city grows and ends up encompassing the basically airport. Now when that happens, generally airport has to change the regulation. When they change the regulation, they go stricter on the engine noise. Basically engine noise would be it could be something else. Again, there are documentation about this, you can read about it online, but the idea would be something like this. Hey, your engine at sea level, basically when you are taxiing, when you are on runway at basically 100 meters from it, it should be 108 decibel. So you can understand, like the requirements become strict. The higher the density, the basically population density around you, the stricter the basically noise regulation would be. So how the heck people do it? Well, you may think, okay, what if I just simply reduce my fuel consumption? Problem is that does not affect sound that much. Like it will affect your thrust definitely, but it will not change the sound that much. So you really can't throttle it. And not to mention, when you are talking about taking off, you need a maximum thrust. So somebody came up with a very clever idea, is that having this kind of nozzle design at the end, where the airflow, now basically airflow that is happening outside of the engine, normal ambient airflow gets mixed with the hot basically system out there. Now it does reduce the sound, however it does add drag. So somebody came up with this idea, is that when you are at sea level, basically at runway, airport, things of that nature, the ambient air is hotter than what is basically on the upper atmosphere, basically when you are traveling at 50,000 feet. So somebody came up with this, what if we have this design which changes, basically once you start to enter in lower atmosphere, that temperature goes up, it starts to shrink inside, and it increases the mixture ratio. Basically the outside ambient air ends up mixing more. Benefit of that, you have a quote unquote sound barrier, reduces noise. But once you are in high altitude, once the cold air outside starts to cool down, it is expands, so you no longer have engine drag. So basically it does not affect your mileage, it does not add any electronics, any hoo-ha. You have absolute reliability, and that's it. Like as simple as that. So aerospace industry is looking seriously into it, and like right now the designs are very very timid. It's like, okay, reduce the sound level by 3% or 5%. Okay, you don't want to directly try 10-20%. You want to test it out. How does it work? How does it hold up against time? Because time is a very critical thing. So there are many uses of this, from medical industry to aerospace to awesome coffee mugs. Now again, if this is that awesome, like, and we have been making it, we have been using it aerospace industry, why it's not everywhere? Well, one of the simple thing you have to understand, they are ludicrously expensive. Like this sort of film where you can, like, it's completely black, you put your hand, you get your temperature marked out. This can cost hundreds of dollars. Basically, these are very, very expensive like, option. So it's flat out, many people simply can't afford it. So that's the first issue. Then you have to understand this aspect. That is why, like I specified, even aerospace industry is like, let's test it out first. They do not last long inherently because their structures are not hardened. Again, you want their structures to change inherently on a crystal level. It's weak. Otherwise, it simply will not change. It will be permanently deformed. So you want that elasticity, but that inherently means it's very weak. And not to mention, because it's doing again and again, over time it will the bonds will break basically. So it's not long lasting. So basically you buy this kind of sheet, it's not like, oh, I will pass down through my generation, and you're like, hey, my grandpa used to use that. Again, it will become useless in few years, so to say. And they are unreliable, even though it does make sense. Like in case of engine, we have been using it, it's not absolutely reliable. Basically, sometimes, let's say it's a very cold weather, we are landing, and for again, the material was designed to make sure that even negative, let's say 5 degrees Celsius, is supposed to do this thing, it's not doing that. But again, sometimes it could happen. Let's say you are in upper atmosphere and it's cold, but again, it's supposed to be like, let's say minus 10 degrees Celsius. It's not doing what it's supposed to. It's not contracting, basically expanding properly. Things of that nature happen. It's not reliable. Again, reliable over time when I'm saying this. So there are many designs. Basically, people wanted to make baby bottles out of this sort of ink, and the idea was that because we put hot basically formula in the bottles, you have to double check it whether it's cool enough for baby's consumption. So people wanted to use that ink basically where it will be red if it's too hot, green if it's go. Now problem is that what if it gets stuck in green state where it's not switching to basically, and you can roast a child's mouth, and that will not be pleasant. So you can understand that people want this to be absolutely reliable. We are not there yet, and not to mention, even if somebody can figure out how to make it right now, it's too damn expensive. That is why you don't see it everywhere. It's right now a novelty for most people, and for aero aero industry, it's still a beginning stage. So what we can expect in the future? Right now, when you type smart material, most of the time you will find self-healing materials. Basically, the material that bonds itself again. Now, again, why don't we use that if we have already made this? Problem with that, generally, it cannot do it scar-free. There will be a scarring. So what we want is something like this, where you have a basically this is a top view, profile view of a glass. Glass would be wrong thing, basically a window, and you fired a projectile through it. Now there is a hole. What could this projectile be? Micrometeorites in Mars or something like that. So you have a hole. Over time it will heal itself. Right now what the materials we have, they cannot do a complete heal like this. Right now, again, in labs we are doing it, but it's not ready yet. So we want this. Basically, you have a hole, and over time it heals itself. So that is what we want, scar-free healing. Now the moment we achieve that on a mass production scale, basically reliably, not in a controlled environment, basically in anywhere where you have dirt, you have to understand that you fired something through it, it will not be absolutely clean. So you will have dirt particle specks or things that will be trapped there. So you have to figure some way out to whether slowly phase them out, how our body does that. And that is why our body never repairs to 100%. It's always ends up with scar tissue. So once we achieve this, where it can slowly go Wolverine level, then we'll have a next gen thing. Right now we are not there yet. We can see it, like engineers can see it, like we can achieve that. We are working on it, but again, it's still a bit far away. Then longer lifespan and endurance, because these sort of materials, they are again inherently active. When you have something inherently active, it inherently ends up reacting with something. That is why, like oxygen is not something that you will find everywhere unless you have something to replenish it, because oxygen will react with things. So again, you want to use something that is quote unquote reactive, otherwise it will not do self-healing. But again, if it's a reactive, it will end up reacting with something else over time, no matter what you do. So again, we want to improve the lifespan and endurance. Then the cheaper production is the main limiting factor, because even though there are somebody can design a spoon that is like, hey, how hot it is, you can have a coffee mugs and all that. Right now they are novelty because they are too damn expensive. So better production structures and all that, and who knows, in future it is feasible. Right now, and what I'm specifying is feasible is that you have, let's say, a windshield and you're driving on a highway, a stone, like a pebble cracked your window, you go your hotel, you sleep it off, and then in the morning it's self-healing. It can be done. Physics is not denying that. It's just right now we are not there yet, basically, where it's that good. So in the future we'll see a lot of smart material, but it will be a slow change. It will be like slowly. Hey, you will randomly notice your cookware will have that kind of paint where you can figure out what temperature it is. So things will happen, but again, Be calm, it will happen slowly. It will not happen like ta-da. It will take its time. So this was my presentation about smart materials. I hope you liked it, learned from it. In that case, please click the like button, share it amongst your friends. That would be a great kindness to me. And if you didn't like it, didn't enjoy it, I'd urge you to press dislike, press it twice to show me your extra disappointment. And please leave a comment because I reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.